Hello, greeting to you all. My name is A.Malik and I am from Computer Science of Engineering Department, D section. I am here to display my conceptual engineering problem on the subject of design and analysis of algorithms. The topic name is going to be fire station. Let's begin. Problem abstraction, modeling fire station as a facility location problem. Fire station placement is formalized as a variant of the K-center maximal coverage location problem with time-constrained service regions. Each potential station location defines a coverage region bounded by maximum acceptable response time, typically 4 to 6 minutes in urban settings. The objective minimizes the number of stations while ensuring all demand points lies within at least one coverage radius subject to budget and geographic constraints. Stochastic demand patterns modeled via Poisson processors require robust formulations that account for temporal fluctuations in call frequency. Geospatial data integration include road networks, traffic flow, and building density to refine Euclidean distances into realistic travel time matrices. Approximation algorithms guaranteed performance bounds. The metric key center problem admits a two approximations via greedy farthest first traversal optimal under P is not equal to NP assumptions. Local search heuristic achieve 1 plus sigma approximation for capacitated variance when swapped neighborhoods are polynomially bounded. Primal dual schema yields big of log n approximation for set cover based formulations by iterative buildings, feasible solutions, and dual certificates. Randomized rounding of LP solution provides probabilistic guarantees on coverage with high likelihood under independence sampling. Recent work established hardness threshold. No polynomial time algorithms achieve better than 1.822 approximation for general metric facility location unless P is equal to NP. Scalability challenges handling city scale instances. Metropolitan areas generate graph with millions of nodes and edges, rendering exact shortest path computation prohibitive for repeated coverage evaluation. Landmark based ALT and transit node routing exploit hierarchical road structure to prune search spaces by orders of magnitude. Parallelization across GPU architectures accelerates all period shortest path using CUD optimized implementations of fluid Warshall variants. Clustering demand points via k-mean or DBS scan reduce problem size while preserving spatial fidelity through representative centroids. Distributed computing frameworks, for example, Apex Spark, enable the composition of location models into geographic partition subproblems. Data-driven enhancement integrating historical incident logs and predictive analysis. Historical fire and EMS call data inform spatially explicit demand density using kernel density estimation with adaptive bandwidths. Spatio-temporal point processors such as self-excitement Hawks models capture clustering behavior where past incident increases near-term risk. Graph neural network embed road network topology to predict future hotspots by aggregating neighborhood risk signal over time. Counterfactual analysis estimates the impact of hypothetical state station placement using causal inference framework with propensity score matching. Digital twin simulation validate algorithmic proposal under synthetic but realistic scenarios calibrated to observe system dynamics. Robustness and resilience, planning for disruption and failures. Facility interdiction models access vulnerability by simulating worst case station closure due to disaster maintenance outages. K-vertex connectivity in the service graph ensure alternative coverage path exists even after removal of up to K-1 stations. Redundancy is explicitly encoded via p-backup constraints, requiring each demand points to be covered by at least p distinct facilities. Recovering algorithmic dynamically repositions mobile units or activate reserve stations when primary coverage is compromised. Game theoretic formulations model adversarial disruptions, yielding, yielding minimax optimal deployment that hedge against strategic threats. Recent advances, quantum and hybrid classical quantum approaches. Quantum annealing explored facility location energy landscape using D-wave systems encoding binary decisions into qubit states wide with quadratic interactions. Variational quantum agent solvers VQE approximately ground stations of Ising models derived from quadratic unconstrained binary optimizations QBO reformulations. Hybrid solver decompose problem into classical subroutines for constraint handling and quantum coprocessors for combinatorial search. Tensor network methods compress high-dimensional solutions spaces, enabling exact enumeration for structured sparse instances. Despite current hardware limitations, theoretic speedup are proven for specific graph classes under quantum query models. Case study: optimal redeployment in Metropolitan Fire Department. A 2023 study of Tokyo fire response system reduced average response time by 18% using column generation to solve a capacitated multi-period location model. Integration of real-time traffic APIs from Google Maps enable dynamic edge weight updates, improving dispatch accuracy during peak hours. Equity-aware constraints prevent service degradation in low-income neighborhoods despite overall cost minimization objectives. Sensitivity analysis reveal diminishing return beyond 6 stations per million residents, guiding budget allocation policies. Deployment use a digital twin simulator to validate performance before physical implementation, avoiding cost real world trials, urban problem and future directions, developing sublinear time approximation schemes for streaming demand data remain unresolved, requiring new sketching techniques for spatial coverage. Federated learning frameworks could enable privacy preserving collaborations across jurisdiction without sharing sensitive incident records. Integration with autonomous vehicle fleets introduces new routing modalities with non-standard kinematic and communication constraints. Casual discovery methods may uncover hidden confounders, for example, socioeconomic factors that bias purely correlation demand models. Standardized benchmark suits akin to TSPLIB are needed to compare algorithmic advance across diverse geographic and operational contexts. Thank you.